Okay, good afternoon, everyone. Yeah, we shall start. Okay, so again, just I'll repeat. Our final exam will be on April 30th from 3:30 to 5:30 in this classroom. Please make sure to come in person. We're very unlikely to schedule makeup exam if you happen to miss that. And we have released a mock exam paper in Canvas. So if you got a chance, feel free to take a look at that paper. It's basically the same structure, but of course the problems, the numbers will be totally different. But you can try to solve the problems in this mock exam paper to get a clue. And we'll release the answers for the mock exam next Monday. And I think next Tuesday will be our final lecture. We'll major focus on reviewing and walking through the problems in a mock exam. I hope everyone could happily spend some time happily going through this remaining short time of the semester end. And we also have a due for homework 6, I believe, on next Friday. So please spend your time and try to submit it in time. It's very unlikely for us to make some personal extension for homework 6 because it is really near the end of the semester, and there's really no execution for you to upload your final grade later. Every year, every semester, the university put a very hard deadline for uploading the final grades. So that makes our flexibility very limited. It's not like other previous homework assignments. We probably can talk about personal extension if you do have some excuses for that. But for the final homework 6, it's very hard. So please allocate enough time and make sure you won't lose your points due to some late submissions. And also for the final exam, so previously we thought, okay, probably we need everyone to just come and do everything blindly, but due to many requests, and now we change our policy. You can bring one A4 paper with cheat sheet. I mean, you can write down whatever formulas and equations you feel that might be helpful, but just one A4 paper, and you need to hand it along with that cheat sheet. Handing the exam paper along with your cheat sheet together for our grading. Okay, any question regarding, yeah. You can use both sided, but you can only use one, one page. Actually, you can view it as 2 pages, but just one piece of A4 paper. Other questions? Yeah, we'll make an announcement to make sure everyone, including those who do not join our class regularly, to see our policy. You are free to bring just one A4 paper, which you can selectively write down whatever possible equations or formulas you felt useful. Okay. So, okay, today we're gonna finish up the hypothesis testing. But again, hypothesis testing won't be covered by our final exam, so don't get panic if you feel uncomfortable in digesting those content. But here, but I wouldn't say that hypothesis testing is not important. It is actually important. and it's actually a very deep topic. Here, we just want to make sure everyone gets the clear intuition of hypothesis testing and why people do this and what's the intuition of doing this, right? And we're going to introduce the several commonly used hypothesis testing techniques, including p-values, to give you the sense. And in the future, if you want to do some like a more thorough study, experimental design, hypothesis testing, this will be a very good starting point. Okay, so our intro to hypothesis testing start with an experiment did 200 years ago. Oh, no, not 100 years ago, 150 years ago, I guess. And it was introduced by the pioneer statistician, Britain statistician R. Fisher, and he was motivated by using some experiment to examine the statement of a lady, right? Yeah, because in Great Britain, people love drink teas. Right? It's not like here people love drinking coffees. In Great Britain, like people love drinking teas. Right? So a lady claimed that she could tell, you're making up a tea, whether the milk was added first or tea added first. Right? So it's kind of like amazing. Right? At least I don't know. Even for coffee, I cannot tell you put milk first or put sugar first. Right? But anyway, Fisher was curious about the latest statement and decided to design an experiment. Right? He kind of like random. He kind of like made up like 8 cups of tea. Right? Those cups are the same, but 4 random cups of teas were made by adding milk first and then tea, and the remaining 4, the other 4 with tea first and then milk. Right? And then he presented these 8 cups to the lady, and the lady tasted every, use a spoon to taste every cup and give her prediction. And surprisingly, the lady's answer about this order is correct, or was correct for all 8 cups of tea. So now comes the question: is R. Fisher's turn to analyze these experimental results and decides whether we should confidently accept the lady's claim that she is indeed have some kind of like a superpower and differentiate the order of adding tea first or adding milk first, or she's just wins by totally by luck. So that's the original that's the origin of the hypothesis testing. And to do this, like Fisher made a so-called null hypothesis. In mathematics, it is denoted as H0. So what does H0 mean? It says, right? H0 says the lady is just guessing. That kind of like face the most ordinary people would expect, right? Because most people won't assume they have the capability to differentiate these orders, right? So, and then Fisher tried to find evidence to either reject the null hypothesis, H0, or accept it. How did he do, right? So the idea is that, okay, let us assume our null hypothesis is true. That is, the lady indeed is just random guessing, right? So that means her conclusion or her results or her prediction is simply by randomly choosing 4 cups out of 8 cups, saying that, okay, for these 4 cups, milk first and then tea. And for the remaining 4, of course, it's tea first and then milk. And then we know that choosing 4 out of 8 cups would give you total 70 possible combinations, right? And the lady correctly identify orders for every cup of tea. And that means like all of the 70 combinations, and she by random chance just pick up 1 combination which is correct. So what's the chance of she successfully do this random guess? Without any additional assumption, this chance is 1/70. Just 1.4% chance. So this is the result. This is the analysis result, right? Based upon your experimental outcome, right? Your experimental, and Fisher, based upon that, and decided to reject the null hypothesis. In other words, we don't believe that the lady guessed those order, milk tea order, simply by chance. And we have high confidence to believe the lady does have some like unusual capability that she can taste and tell the milk is added first or the tea is added first. And why did Fisher reject the null hypothesis? Yes, exactly, right? That's the key, right? So if we assume the null hypothesis is correct, right? And then based on this assumption, you can make some probabilistic statement. You do some analysis, you calculate the probability that the lady correctly identified the order for all 8 cups. You found, okay, this chance is really low. That brings us some warning, right? So if H0, H null hypothesis is really true, right? And then your experimental outcome should be some very likely, some event that are very likely to happen, right? It shouldn't be some rare events. In other words, the underlying, this analysis implies that for any probabilistic model, if you just do one experiment, it is very, very unlikely to see a rare event. If you happen to see that, that means your basic assumption, your model is wrong. Right? For example, if you assume your some random variable follow some standard Gaussian distribution, we know that standard Gaussian distribution will have 0 mean and variance 1, right? Now you just observe one value of this random Gaussian distribution. It's very likely that your observed value is close to 0, right? But if you happen to say, okay, your random variable, which is supposed to follow standard Gaussian to be very large, say 100, that brings issues, right? Because if we just do one experiment, it's very unlikely to see such a rare event on the line under the standard Gaussian distribution. That implies that there's very, very high chance that your underlying assumption, the random variable following standard Gaussian, is wrong. It must follow some other distribution. Does it make sense? Any question regarding this analysis? Okay, yeah, this is very, very important. I mean, when you look deep in the hypothesis testing, you will see a variety of different statistics and distributions and calculations, p-values, and seems like so complicated. But all of them are just respecting the same principle. That is, if you assume the true distribution is like this, according to the true distribution, what you observed is some kind of rarely happened event, then this distribution assumption is wrong. You're going to reject it. That's the key idea of the key method of hypothesis testing. And then the remaining, the details, you execute hypothesis testing. It's just about, okay, underlying which which distribution you're going to use, right, for your null hypothesis. And how do you make up the statistics to decide the events? And under what kind of significance level or confidence you're going to reject null hypothesis and all those kind of stuff. Question? Great. So let us summarize the process of hypothesis testing. So first, we're going to define the null hypothesis. Of course, this is a problem dependent. It depends on which kind of like conclusion or statement or claim you want to verify. And usually the null hypothesis represents some kind of like a default explanation on interesting things and even some kind of like common sense, meaning most people will believe that. And sometimes like this kind of common sense are not necessarily correct. And second step is that we're going to assume your null hypothesis is correct. And based on that hypothesis, we're going to derive some probabilistic model. In most cases, it will be some like distribution, PDF or CDF, whatever. Right? And third, we do some kind of experiments. We do some testing, we do some observation, we do some measurement, and then based on our probabilistic model, we'll calculate what's the chance, what's the probability you're going to observe those outcomes. So after we get this probability, right, if we find that under the null hypothesis, the observed outcomes correspond to a rare event, meaning that if you assume your hypothesis, your default hypothesis H0 is correct, then your observed outcomes could be viewed as a even very unlikely to happen. Then we should reject the null hypothesis because our practical principle would be, okay, a rare event should never be observed in just one experiment. This is a whole process. Question? Great. So let us look into this step by step, right? Step one, we formulate the hypothesis, and we usually denote the hypothesis by H0, right? And the corresponding or in contrary to the null hypothesis, we're going to propose a complementary hypothesis, which we call H1. So H1 usually represents those novel claim on usual conclusion and bold statement and those kind of stuff. And once we have identified what our null hypothesis H0 is and what the alternative hypothesis H1 is, in step two, we're going to design some experiment. But for short, the experiment essentially is just to do some kind of like measurement or observation over a set of random variables. And you're going to have a set of random variables. We usually denote it as a random sample, right? And then based on the random sample, we define a test statistics T. So again, here we want to emphasize again, the statistics is a function of random variables, right? It's a function of the random variables you try to measure or observe your experiments. So the test statistics itself is also a random variable. Okay. And then to decide some kind of confidence, right? We need some kind of confidence level based upon which we're going to reject the null hypothesis or accept or accept the null hypothesis. So we call this level as the significance level. Like we usually denote it as alpha. Okay, and then in step 3, which is omitted here, is just to calculate the value of the statistics and look at this value of statistics is bigger than some critical value decided by alpha. If this test statistics is bigger than critical value decided by alpha, then we'll view our experiment results is considered as a rare event. Then we're going to reject the null hypothesis H0 accordingly. We reject null hypothesis H0 with significance level alpha, or alternatively, we could say we accept the hypothesis H1 with significance level alpha. Question regarding this general description about the hypothesis testing process? Okay, so let us look at some example, right? So here is one example. If I want to test the parameters regarding mu, which is the Gaussian distribution, right? So the mean parameter is mu, right? So we can use sample mean as our statistics. And based on sample mean, we do some kind of shifting, right? We have sample mean subtracted by mu and divided by the standard deviation over square root n follows standard Gaussian distribution, and with which we can compute the critical value, which comes from the mu plus the z alpha plus times sigma over square root n. This is very similar to the confidence level. Then what should we do, right? We run an experiment. That means we're going to collect a set of random variables, x1, x2 throughout xn. Right? Then we compute the test statistics. We're going to compare the test statistic value with our critical value, T alpha. And if T is bigger than T alpha, we're going to reject hypothesis H0. Otherwise, we're going to accept it. Going back to this example, right? So our null hypothesis will be some random variable, see, some value follows a distribution, a Gaussian distribution with mean mu and variance sigma square. Right? So mu could be, say, for example, I can make null hypothesis that say the temperature tomorrow with mu follows Gaussian distribution with mu as I don't know 78 and the variance like 5, something like this, right? So now I want to And H1 will be okay. It doesn't follow 78. A Gaussian distribution with mean 78 and variance 5. So how do we verify? How do we conduct our hypothesis testing? Like we can see tomorrow, we can just look into the temperature, right? You can set up several measurements, right, at different places in campus. Right? You're gonna collect a set of measurements x1 to xn, and we're assuming okay, they're ideal, meaning independent and identically distributed. Then we're gonna compute our test statistics. What is our test statistics? Any thought? From what? Yeah. To be more specific, it is here, right? As we just mentioned. We're assuming this temperature or any quantity of interest follow this Gaussian distribution with given mu and sigma square, right? So now we collected n IID examples. So now we first compute the sample mean, which is the average of all the collected random variables values, right? And then we do some kind of shifting, right? This remember, this is a Gaussian distribution. If you do some shifting by subtracting the mean and divided by the standard deviation, it follows standard Gaussian, right? So that is very similar to how we construct the confidence interval. But here, we don't know whether our null hypothesis is correct or not. We just assume, okay, when it is correct, and then let us look into this statistics, right? So our statistics T will be just looking into the shifted sample mean by mu and sigma over square root n. Why we should be divided by sigma over square root n. Why? Any thought? Yeah, if we assume all x1 throughout xn follow this Gaussian distribution, right? And what does the sample mean follow? It's like data by the variance. What about the variance? Yeah, the variance is here, sigma square, right? For every random variable here, for every ID random variable here. And what's the variance for the sample mean? Yeah, sigma square O n, right? Because you do the average, right? When you do the average over set ID random variables, your variance will be divided by the number of samples you average. Right? So if x1 throughout xn follows this Gaussian distribution, I mean, the distribution under the null hypothesis, right? So the average of the same random variables should follow the same mean, right? A Gaussian distribution with the same mean, but variance with variance divided by n, right? And then when we calculate x the sample mean subtracted by mu and then divided by this standard deviation, you're gonna follow a standard Gaussian distribution, right? That's the property of the Gaussian distribution, right? You subtract the random variable by its mean and divide it by its standard deviation, and this transform random variable will follow standard Gaussian distribution, right? Everyone feels comfortable? Yeah, I mean, we have discussed this many times, right? If you feel unclear, you just look into our previous slides, right? It's just the knowing results. So once we have computed this test statistics, right? So we're gonna look at whether T is bigger than T alpha. And T alpha, remember T alpha is what? So this is standard Gaussian distribution, right? T alpha is a critical value such that the probability that your random variable is bigger than T alpha will be alpha. Right? So if we check our statistics value calculated from our experiments, right? You find that actually T is here, meaning that T is indeed that is bigger than T alpha. Then that means we're gonna reject H0. We're gonna reject our hypothesis that all those random variables respect this underlying Gaussian distribution. Why? Why when we say T is bigger than, see, here is T, right? We see our observed statistics value T is bigger than the critical value T alpha, then we're gonna reject H0. And the analysis, how does this correspond to, how does this associate to the principle or intuition we have just emphasized about hypothesis testing? Yeah. And then it's a rare event, right? Yeah. Okay. So thanks for the answers. That's great, right? So alpha usually choose to be very, very small, say 0.05, right? So remember, what's the idea of hypothesis testing? You want to look into the case that under the null hypothesis, whether your observed experimental outcome correspond to some rare event. So you see that you calculate the statistics T, right? And under the null hypothesis, your statistics T should follow a standard Gaussian distribution, right? But then you see, actually, this standard Gaussian distribution, which is supposed to be a standard Gaussian distribution, this T value is bigger than T alpha. That means it represents a rare event because for a standard Gaussian distribution, its random variable's value, its chance bigger than T alpha is only alpha, right? See, 0.05 if you choose alpha to be 0.05, right? So that means this event happens with the chance it's just 0.05%, of just 5%. That's very unlikely to happen in just one experiment. That means, okay, your assumption probably is wrong, right? It's very probably this T statistics doesn't really follow a standard Gaussian distribution. It should follow other distribution. And that means your null hypothesis is wrong. And we're going to reject H0. 0, meaning that we think your null hypothesis is incorrect, and those values shouldn't follow this particular Gaussian distribution. Question? Okay, great. So beyond the significance level, there's another commonly used statistics. It's called p-value, and maybe you have heard a lot, right? So what does p-value mean? P-value is just the probability based upon your observed statistical value. So suppose this is your observed value of t, your statistics, which could be, say, 2.98, right? It's bigger than the critical value T alpha you choose, right? And in our previous example, our example we just discussed, right? We just look at if this observed T statistics value 0.98 is bigger than our given critical value T alpha, right? If it's given, we say, okay, we observe one event that your statistics falls in the region that is from T alpha to infinity, right? And the chance for a standard Gaussian distribution following this region is very low. It's just alpha, see 0.05. So you view, okay, this is a random event, so we're going to reject. This is one way of doing that, right? So our alternative way of doing that is that, okay, we're not looking at T alpha. I just want to say, what's the chance that for a standard Gaussian random variable, x falls in the observed statistical value and infinity? This actually summarizes how extreme this observation is, right? We just calculate based upon your observed t, how likely a standard Gaussian random variable will be beyond t. If this probability is low, the lower the probability this, it indicates the more extreme you observe for t, right? And in any case, more rare you observe this t given your null hypothesis is correct. Like, let me repeat again, right? So an alternative way to calculate the test statistics is that, okay, I'm going to first calculate t, right? And following the null hypothesis, this t should follow standard Gaussian distribution. And throughout the kind of experiments and calculation, I got, okay, my observation of t is 0.98, right? And next, based on this t, I'm going to calculate the probability a standard Gaussian random variable x falls out falls in t and infinity. What's this chance, right? See, 0.07, right? And this chance, this probability, that is this area under, this green area, under this red curve, indicates how extreme the value of t you observe, right? And the more t is toward the the infinite level, right? The more extreme you observe about t, right? If your null hypothesis is correct. So actually, this probability also represents a kind of like measurement about how extreme or how rare you observe your experimental outcomes. And then we can decide whether we're going to reject the null hypothesis based on this probability. So this probability is called p-value. Any question? Everyone feels good or everyone feels confused? Okay, I'm more optimistic, right? So okay, I assume everyone gets the idea, right? But you can view like p-value is just another way to calculate or to measure under H null, under null hypothesis, the rareness or the extremeness of your observed outcomes, right? Of course, this extremeness or rareness measurement beyond some threshold, I'm gonna say, okay, it is not plausible to see that, right? So I can reject null hypothesis, right? So this is called p-value, right? Also, you can define a thresholding level alpha, and when p-value is less than alpha, we're gonna reject H0. Okay, so let's rest for a while, for about 5 or 6 minutes, and let's continue. Mhm. You mean the final?
On the final?
No, I won't
Okay.
come.
Because I just saw there's a practice problem in the practice exam, so I just wanted to make sure that.
If you want to do that, feel free to
Okay.
do that. But
But
we
it's not
won't
here.
cover,
Okay.
yeah.
I just wanted to make sure.
Yeah. Okay, so let's continue. So far we introduced the two types of statistics to do the hypothesis testing. One is that just based upon uh, the values of the random sample, and you calculate statistics, and then you look at the distribution of your statistics, which is supposed to follow underlying the null hypothesis. In here, most commonly used is just Gaussian, standard Gaussian distribution. Then you see whether your statistics value, like for outside of some given critical value, it is bigger than the critical value. It means that you find some rare event. This event, if the null hypothesis is true, the probability to happen should be just alpha, right? But if you find this event happen, that means, okay, your experiment give you a rare event that is unlikely for just one experiment. So we should reject null hypothesis. And another way to do the calculation is to calculate the so-called p-value, right? So p-value not only calculate the statistics, but also you're going to calculate what's the probability a standard Gaussian random variable falls out your observed statistics, right? So if your null hypothesis is correct, then your test statistics should follow standard Gaussian distribution. And you observed test statistics say is 0.98, then the chance that your random variable, which follows the standard Gaussian distribution, is bigger than or equal to this statistics is very, very low. And this probability summarizes or measures how extreme or how rare you observe such experimental results. This is called p-value. If p-value is less than some given significance level alpha, we're going to reject H0. In other words, we're going to accept H1. Otherwise, we're going to accept H0. Okay, so next we're going to look at a more general case, which is similar to confidence intervals, for which we do not know the variance. So again, our hypothesis testing, the subject or the statement still will be, okay, the random variable x, right? Or some kind of quantity of interest has a particular, has a particular mean value, which could be, I just random write it, say 3.3, right? So, but I'm not gonna assume I know the variance for this quantity of interest, say the stock price or temperature or precipitation amount. I don't know, right? I just want to, I just want to say, I would just want to claim that, okay, this quantity of interest, its mean is 3.3. I want to test whether I should reject this hypothesis or not, right? So again, to do the hypothesis, right? To do the hypothesis testing, we're gonna collect a set of ID random variables x1 through the xn, which are some kind of measurement of this quantity of interest, right? Their ID. So now that the variance is unknown, we're gonna calculate not only the sample mean, but also the sample variance, right? And then we're gonna shift the sample mean by our guess mu, right, which is 3.3, and divided by sample standard deviation over square root of n. What does this statistic supposed to follow? What is this statistic supposed to follow? We talked about this about in a confidence interval, right? Yeah, I mean, if H0 is true, right? And but we don't know, we just know its mean is 3.3, right? We don't know its variance. Now I just collect a set of ID random variables, right? I calculate sample mean and sample variance. And now I calculate this t, right? This t, h is just to subtract the sample mean by mu and subtract and divided by the sample variance square root over square root of n. And what distribution is supposed to follow? It's student t distribution, right? Is what you want to say? Yes. Is that exactly the same as we discussed about confidence intervals, right? If we know the variance, okay, we can safely using Gaussian, right? But if we don't know the variance and we replace the variance by our estimation of variance, which is sample variance, right? Remember, sample variance is 1 over n minus 1, summation from 1 to n, and xj subtracted by sample mean take square, right? This is called sample variance. If we replace the true variance by the sample variance, then this statistics should follow a standard student t distribution, right? And that means, and with some degree of freedom. Remember, this is a difference from the student t distribution, right? In addition to mean and variance, you also need to specify the degree of freedom. And here, because our sample size is n, so the degree of freedom is n minus 1. Right? And similarly, the critical value for the t distribution will be, say this is t distribution, right? Remember, t distribution always has a thicker tail, right? It's t distribution. Sorry. This is T alpha, right? This T alpha is the place such that this random variable T bigger than or equal to T alpha is alpha. Okay. And remember the critical value for T distribution is different from the critical value from the Gaussian distribution. And T distribution usually has a smaller critical value, right? Why does it have a smaller critical value? I mean, for the same alpha. It's because T distribution has fatter or thicker tails, right? So you got, if you compare it with a standard Gaussian distribution will look like this, right? So that means like it has a thinner tails. So if you want to get the same value, right, your Z alpha should be here, right? And T alpha will be out of set, right? So, but anyway, the way to do that is the same, right? The only difference is the value, right? So if you look at your T statistics, right? And if you find that, okay, it is beyond the critical value T alpha, right? This is your observation of T, right? If it is bigger than T alpha, that means you'll find some event happen. That event is that a standard student T distribution's random variable falls out of T alpha. That basically means like you have observed a rare event, and this event has the chance just alpha. So then we should reject the null hypothesis. And it is not your mean, right? The 3.3 is not a mean. Otherwise, you're gonna accept your null hypothesis. And of course, you can also calculate the p-value, right? So the p-value, as we mentioned, is just you just calculate probability based on your observed value for this t statistics, right? You just calculate the probability. What if your standard student t random variable is bigger than or equal to your observed t value? Say this could be 3.98, right? If it's bigger than 3.98, what's the value, right? This is the p-value. And also, you can look into this probability. If this probability is less than a given alpha, then we could say, okay, we're gonna reject the null hypothesis because your observation is too extreme for your assumption. Question? I hope you can find the correspondence, right, between the confidence intervals and hypothesis testing, because the calculation is almost the same. You calculate the statistics when you know the variance. The calculation is just to subtract your sample mean by mu and divided by the standard deviation over square root of n. Otherwise, you're going to replace the variance by the sample variance, right? And then you're going to use the critical value for t distribution rather than the standard Gaussian distribution to execute the hypothesis testing process. And how do we get to those critical value, right? How do we get the p-value? Okay. So here's the example using R. Of course, you can open any statistic book and look at the dictionary, but here is easiest way of doing that. You can just search on Google like R library online or R platform online. You click into the web page, and in the command line, you just type 1 minus PT just means like p-value of t, right? T distribution with your observed t statistics, which could be whatever value you get from your experiments, say 3.98, and you specify the degree of freedom, then you can calculate the p-value. So once you get the p-value, you just look at whether the p-value is less than your given threshold alpha, right? If it's less than threshold alpha, you're going to reject the hypothesis H0. Otherwise, you're going to accept H0. Question? Okay. Yeah, if you're interested, you can take a look. You can search on the web or take a look at the reference book for a class. You can look at the bibliography of Ronald Fisher, Fisher's exact test, and also hypergeometric distribution. This distribution is used to more precisely characterize the probability that the aforementioned lady testing experiments, if she just do this randomly, what's the probability, right? We just use a very simplified model to describe this and trying to give you some intuition. Okay, so the last diagram, which kind of very well summarize this hypothesis testing process, which worth you reading and looking into that. Actually, if you can memorize this figure, you don't need to check out our slides, right? So basically, our null hypothesis, to summarize the examples I've seen so far, we have our null hypothesis, right? Which follows some Gaussian distribution with mu. Mu is given, say 0.78 or 3.3, something, whatever, you name it, right? We consider two cases, right? The first case is that, okay, I know, I assume the variance is known. Right? And I just want to test whether its mean is some particular value, say 3.8, right? And then this is null hypothesis. And then the alternative hypothesis is that, okay, it follows another Gaussian distribution, but with a different mean parameter, mu prime, right? So how do we do that, right? We just calculate the statistics, right? And this statistics is just to subtract the sample mean by your assumed mean, mu, and divide it by the standard deviation, by square root of sample variance over square root of n. And if your hypothesis, your null hypothesis is true, and this t should follow some standard t distribution. And then we just want to look at, of course, you're going to give some like a degree of freedom. It depends on how large size of your random sample. Right? And then you just look at your observed t here, for example, here, right? I'm going to use. This is your observed value, right? So there are two ways to decide whether you're going to reject your null hypothesis. First, you specify this significance level alpha. Then you look at the critical value for the standard t distribution, which is t alpha, right? And if your observed value for the statistics t here is bigger than t alpha, that means you observe some event, which is rare in that the probability you see this event should be just alpha. And then you're going to reject null hypothesis. Right? And the other way of doing that is that you're going to further calculate what's the probability for standard t distribution random variable will be bigger than t, right? Will be bigger than t. What is this? Standard t distribution will be bigger than your observed t value, right? So this is called p value, right? If this p value is less than your given threshold alpha, we also reject the null hypothesis. And this kind of like figure and framework also applies to the case where your sigma, your variance is known, right? The only difference is that, okay, now you're going to assume this is a standard Gaussian distribution. The statistic, the critical value here is for standard Gaussian rather than t distribution. But the process is the same, right? You either look at whether your observed statistic value is bigger than the critical value, or you just look at the p-value calculated based on your observed statistics. Right? And then you decide according to your threshold alpha. Any question? Everyone feels good? Yes, capital T is the statistics, right? It's a function of the ID random variables we collected, right? And now what you do is you're going to do some experiments, right? You're going to have evaluated all the random variables you get, and then you evaluate your capital T. This value is denoted by this lowercase t, right? This could be 0.8, right? Or 0.9. You just want to check, okay, you observed this value, whether it is beyond some threshold. Other question? Okay, again, although this won't be covered in our final exam, but I hope everyone will really get the point here. And what's the intuition, what's the strategy, and what's the and also the basic ideas like involving Gaussian distribution or student t distribution and what's their cases, right? And this will be really helpful in the future because in many decision scenarios, you do need some kind of hypothesis testing and with which as your basis to make decisions. Okay, I guess we can stop earlier today and see you on next Tuesday. And remember, please take some time to practice your mock exam, and we're going to walk through the exam problems next Tuesday. Okay, see you on next Tuesday. Yeah.